Hi everyone, here is the promised PowerPoint limits at infinity. You'll find that just a couple of things that I mentioned in class will reveal themselves here. So we're going to determine finite and infinite limits at infinity so that you might have possibility where the limit is finite or I get a value that's infinite. The limit doesn't exist or it goes to infinity. And determining horizontal asymptotes if any of the graph of the function is really the basic premise, right? Horizontal asymptotes are where the graph flattens out and approaches as x gets larger, 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 or x gets smaller, smaller, smaller. So here's this function, probably, not one that we have off the top of our head in terms of what the graph of 3x squared over x squared plus 1 looks like. But here it is. Here's the graphical representation. And you can see as x gets larger, 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 the y values are getting larger, except at some point they start to flatten out. And it looks like it's approaching this limit, which would be a horizontal asymptote. As x is going to negative infinity in this direction, the y values are increasing and then they start to flatten out. So we can see on our table, right, negative 100, negative, you can see as, well, let me start at 0 and then go to the left, right? X is getting infinitely smaller, 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 and I can see from these y values approaching, getting closer and closer and closer to 3. Same thing to the right, getting closer and closer and closer to 3. So how do I say this? Well, we know what this looks like in terms of the function notation. Nothing we don't already know, but now the limit as x approaches negative infinity or x approaches positive infinity. So this is directly out of your book. I was just going to try to blow this up. Actually, this is from your pre-calc book. Definition of horizontal asymptotes. Right, this is section 2.6 from your pre-calc book. And this right here, when I have the limit, not the limit, of horizontal asymptote, when n is less than n, where's n and where's m? N is your numerator, n for numerator, m for denominator. And so when n is less than m, the x-axis, or y equals 0, is the horizontal asymptote. When n equals m, we talked about this today in class, the line y equals a sub n over b sub n, that's the coefficients of the leading terms, and it is the ratio of those coefficients. That's where the horizontal axis asymptote exists. And then there's another scenario where the numerator degree is larger than the denominator degree, and there are no horizontal asymptotes, and you'll see in each of these cases. So how is this different? Well, with limits, if the degree of the numerator is less than the degree of the denominator, the limit is equal to 0. That's your horizontal asymptote from the previous course, from the previous slide. If the degree of the numerator is equal to the degree of the denominator, then the limit of the rational function is the ratio of the leading coefficients. And then the third scenario, if the degree of the numerator is larger than the degree of the denominator, then the limit of the rational function does not exist. Now, we talked a little bit, my example today was the limit as x approaches infinity for 1 over x. Here, we're generalizing. We're saying there's a rational number, where r is a rational number, it's x squared, x cubed, just x, and c is a real number, So this is more of a general form. It could work when x goes to positive infinity. It could be when x goes to negative infinity. It does not matter. So here I have this situation, the limit as x approaches infinity of 4 minus 7 over x squared. So you may already see what the answer is, but the process is, don't forget, I can take this and separate each of the terms. The limit as x approaches 4. 4 is just a constant. The limit as x approaches infinity of 7 over x squared. You're not plugging in infinity. This is not something I want to see. I don't want to see 7 over infinity. Okay, because infinity is really a concept. So no, I don't want to see that. I just want you to understand that the denominator is getting larger, larger, larger. The limit is going to equal 0. So this is just a constant 4. Limit is equal to 0. Final answer is 4. No need to plug in, no need to write any more work. This is to be understood at this point. The denominator is getting bigger and bigger. That means the fraction, the value of the fraction is just collapsing to 0. Oops. Okay, so in this problem, there is that easy root, right? We just talked about it. Well, the degree of the numerator is 1. The degree of the denominator is 1. The limit is equal to 2/3, okay? Because that's where the horizontal asymptote occurs. That's the same concept in terms of limits. But there's another strategy that I want to talk about. We already know the answer to this, so it makes sense to look at a different strategy. I could divide by the highest power of x. What does that give me? It does get a little bit more complex before it gets a little simpler. But when I divide every term by the highest power of x, you can see 2x divided by x, 1 divided by x, 3x divided by x, 1 divided by x. This breaks things down into this concept of c over x to the r. And I simplify this. I get 2 minus 1 over x. I can't simplify that. 3, that simplifies. And then 1 over x, that simplifies. And then I can actually take the limit of the numerator and take the limit of the denominator. This piece right here, the limit as x approaches infinity, the denominator is getting larger, larger, larger. That equals 0, right? This is just equals 0. This equals 0. Final answer, 2/3, which I knew from the beginning. However, the strategy you'll see is going to come in handy when it's a little bit more complex. Okay, so these two problems really pertain to the other two properties. The degree of the numerator here is 1. The degree of the denominator is 2. I should have a horizontal asymptote, or the limit should equal 0. And so I'm going to put that's the easy route to go, but I'm going to do my strategy. Divide everything through by the highest power of x. So I have 2x over x plus 5 over x, all over, it's x squared is the highest power of x, right? 3x squared over x squared, highest power of x, plus 1 over x squared. So it's the limit as x approaches infinity. So what happens here? Let's simplify. I get 2 over x plus 5 over x squared. Denominator is 3 plus 1 over x squared. Limit as x approaches infinity. So let's determine, this is 0. This is 0. 0 plus 0, obviously, I get 0 in my numerator. I get 0 here over 3. Check. Okay, so my strategy, obviously I knew the answer to begin with. However, I want to just play with this strategy a little bit. The second one, the strategy is also comes into play. The degree of the numerator is 3. The degree of the denominator is 2. The numerator is larger than the denominator. This would say there are no horizontal asymptotes, or the limit goes to infinity. So let's divide by the highest power of x. 2x cubed over x cubed plus 5 over x cubed all over 3x squared over x cubed plus 1 over x cubed. And I'm still doing the limit as x approaches infinity. So let's take a look at this. Okay, this cancels, so I have 2 plus 5 over x cubed, which that goes to 0. So I have 2 in the numerator, and I have 3 over x plus 1 over x cubed. So here, the denominator is just doing what? It's getting smaller and smaller and smaller because both of these are getting closer and closer to 0. So where the denominator is getting smaller, 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 that means the value of my function is getting larger and larger and larger. Okay, so sometimes there's that mind analytical component that helps you get to the answer, right? I'm not going to plug in infinity here, but I understand this is getting denominator is getting smaller and smaller. When the denominator gets smaller, the value of the fraction gets larger. Okay, so I'm going to post this 22 to 34 even, page 205, all limits at infinity, and I think you'll be fine. This isn't crazy, something you've never seen before. So this makes a good video lesson, and